Okay, so today is a continuation of the last video. In that video, we calculated what the envelope is for all possible trajectories of projectile motion for all different possible launch angles theta, but at a fixed v naught, at a fixed launch speed. And we found that all possible trajectories have to obey this inequality. So this red dotted line here, which is the envelope of all trajectories, is given by another parabola. This r star is the maximal range of the projectile, which is just v naught squared over g. And we've got another question to answer today. So here we'd like to calculate what is the volume of all possible points in space reachable by this projectile with a fixed v naught. In other words, if I can swing this cannon around in any direction, any vertical angle or any polar angle I want, any azimuthal angle I want, what's the total volume of space that I could fire a projectile into? We're going to do this two different ways. So first, I want to calculate the volume of this envelope using good old-fashioned calculus, just as a little bit of calculus review. And then I want to take a look at an alternative method that's maybe a little bit more classical in nature, which is to use Cavalieri's principle. No calculus involved. So let's do the easy calculus first. I want to take this region bounded by this red dotted line. Hopefully everyone can see that. And I want to revolve it around the y-axis. For those that have had Calc 2 or something equivalent to that, this should make you think of maybe using the shell method, the cylindrical shell method. I'll chop this space up, orange here. I'll chop this space up into a whole bunch of little tiny strips. These little strips will have a little width, dx. They have a distance from the axis of rotation, which is simply x. And they have a height, which is y. In fact, this specific y, up to that red line. And the idea behind the washer method is to say, oh, well, the volume should just be the volume of each little cylindrical shell when I wrap this around, integrated over all possible radii of those shells. So this little shell is going to have a radius of x, a height of y, and a thickness of dx. So the volume of this little shell revolved around should be 2 pi times the radius of this little shell, which is just going to be x. Of course, we'll be integrating. That's the circumference of my shell that's being created here. And I need to multiply it by the height, which is y, and then integrate it dx, because that's the thickness of this little tiny strip. We want to integrate over all possible x's from 0 all the way out to r star. Not too bad. Using the result we found last time for the height of this region that's bounding, we can quickly evaluate our integral. I'll probably go ahead and use the same u substitution we did last time. Using that here, we'll be able to pull out a bunch of constants. The 2 here and the 2 here will cancel. I'll get an r squared that comes out here. I'll also pick up another r star that comes out here. I'll pick up another r star from changing this x to a u, and I'll also pick up a third r star by changing this dx into a du. We're left with a pretty basic antiderivative to perform. Notice that the 0 will give us a 0 when we plug in our fundamental theorem of calculus, and the 1 will be pretty trivial too. One half minus 1/4 will be 1/4. So we end up with this value for our final volume. This is the total volume that is obtained by firing my cannon into any direction I want with a fixed speed v naught. Okay, that gives us our first result. Now let's try doing this in a slightly different way using Cavalieri's principle. Okay, on the board I've drawn two different paraboloids of revolution. In the first case, we have a standard upwards opening paraboloid governed by the equation, we'll call it y1, h x squared over r squared. Notice that this paraboloid can be inscribed in a cylinder that has a radius of r and a height of h. Indeed, if you plug in x equals r, we do end up getting y equals h, so this is actually bounded by a cylinder. And then I have a second paraboloid, which is inverted. It's the same basic shape, but it's upside down, meaning we have when x is equal to r, I'm down at the bottom, that's a root. When x is equal to 0, I still have that same height h. So it is circumscribed by the same cylinder, the same height h and radius r cylinder. Now what we'll be using here is Cavalieri's principle. This is a mathematical fact that comes from Italian mathematician Cavalieri from, I think, I want to say 15th century. And the idea is, if I have two solids that have the same cross-sectional area for every possible slice, so if I take a cross-section through both of these at some given height, and they have to be maintained in their orientation, and I take some slice through them, if they have the same total cross-sectional area at every possible slice, then the volumes of the two solids have to be equal. This is a useful fact when we're talking about things like oblique cones or oblique cylinders, where they may not be right cones or right cylinders. The axis might not be perpendicular to the base, but as long as everything's just kind of slid over one way or the other, the cross sections at every height are the same, and that gives us the same total volume. So let's see how we might use this to find the volume of really this paraboloid. This is the one we're kind of after because it's got the same shape as our paraboloid up here, by looking at some particular height. So if I take any height, say y, and I just cut through at that height y, what are the cross sections? In this first case, my cross section is a disk, and the area of that disk, which I'll call A1, is just going to be pi times the square of the radius there. Well, I can solve for x, which is the radius at any given height, and I'll end up with the radius here being the square root of y over h r. That is my radius at some given height. So notice I'm just solving this equation for x, multiply the r over, divide by the h, take the square root, and then we should square that so that we get the area of that disk. Okay, so that is the area here. For the other shape, I'm actually not going to look at the area inside of the paraboloid. I'm going to do something a little tricky. I'm going to look at the area outside of this paraboloid. So what we'll have is we'll have an annulus, or a washer, whose outer radius is r, always, and whose inner radius is now the x that we get from solving this equation. So the area is going to be the outer area, pi r squared, that'd be the whole cross-section of the circumscribed cylinder, minus pi times this radius squared. Well, again, solving for x here, I'll divide by the h, I'll subtract a 1, then sort of negate that, and multiply by r. Under the square root, that'll end up being this expression. So that's just solving this equation for x. Divide y by h, that's this. Sort of subtract on both sides, I'll get a 1 minus y over h. That'll be x over r squared. Take the square root of both sides and multiply by r. What's interesting here is if I compare these two areas, this area simplifies quite nicely to just pi y over h r squared. But so does this. When I square this square root out, I'll get a 1 minus y over h. I'll get an r squared. But then I have this r squared minus 1 minus y over h r squared, which is the same. Which means at any given y, these two areas are the same. The area of the disk that's cut through here and the area outside of the paraboloid from the second drawing. By Cavalieri's principle, that means those two volumes are equal. Which volumes am I talking about? I'm talking about the volume that is contained inside of this paraboloid and the volume that is outside of this paraboloid. Those two volumes are equal to each other. But notice that this paraboloid and this paraboloid are the same paraboloid. One's just turned over. They do have the same volume themselves. So this volume is the same as the volume that is inside of this paraboloid, which is also the same as the volume outside of this paraboloid. So those two volumes add up to the red circumscribed cylinder, which means each of them have to be half of that area. So let's write that after getting rid of this. So here we have that the volume in this paraboloid and the volume outside that paraboloid are each half of the total cylindrical volume, which we know is pi r squared h. So going back to our original picture here, the r is this r star. It's the total maximal range of my projectile. The h here is this maximal height in the middle, which you can use our y equation over here to find is half of that maximum r. So putting everything together, we have this for the volume that is contained in this set of points. The 1/2 and the 1/2 become the 1/4 that we saw before with the pi. R star squared times another one is r star cubed. And then we can still replace our r star as before. So we get the same result that we did from calculus, giving us our secondary check that this is the volume of all space that's reachable by a projectile launched at speed v naught. QED.